Well, here we've got a nice multiple choice question, one that's pretty typical for an AP exam. It starts with a curve here that's referred to as the Maxwell Boltzmann curve. The question says the graph above shows the speed distribution of molecules in a sample of gas at a certain temperature. In fact, let me bring a little diagram in right here. And here's a sample of gas, certain volume, and these little molecules are bouncing around. Even though the temperature appears to be constant, all these molecules don't have the same kinetic energy. Some of them are, as you can see with this arrow, are moving very, very quickly, and some have got shorter arrows that indicate they're moving not quite as quickly. Now, the pressure in here is the kinetic energy per unit area of these bouncing molecules, and this curve sort of represents that. We have certain number of molecules here which are slower molecules. Let's pick one that's slow here. That looks like the shortest arrow. And then we have some molecules that are moving very, very quickly. That'll be our longest area. Here's a nice long one. And then we have an average. Now, if this diagram was done right, the number of molecules that have this average speed will be greater, and we'll have a little peak. In other words, there are a lot of average molecules, but there are also some molecules that are going faster than average, some that are moving slower than average, and that's what this curve is about. The area underneath this curve is the total number of molecules, and at any one point, those of you who like calculus, you've got the individual set of specific molecules with that speed. Now on to the right here, you can see I've got a description. This is supposed to be nitrogen, 28 grams per mole, and it has a temperature of 720 Kelvin. That's pretty hot Celsius. The average speed of these molecules is about 740 meters per second. This 800 is really a more sophisticated average that uses the squares and square roots. Those of you who are into statistics would understand the root mean, square, average, whatever they call it. But this is what this is supposed to represent. Nitrogen at 700 K, and this is sort of interesting that everything isn't the same. Even though the temperature is constant, because we have so many molecules, they average out to give us what temperature is, an index of the average kinetic energy of these bouncing little marbles, which are gases. Now, we're going to we're going to cool this nitrogen from 720. And by the way, this is the curve. In fact, look at this curve. This is very interesting. Our average is about 800, which is right about there. A little bit. This peak is skewed. Notice that it's a little bit further to the right. The average is about 800, or 700, 800, depending where you want to end up looking at, whether you use the real average or the root mean square. And that's where this peak is. Now, we've got some molecules here that are traveling at 1700 meters per second, and some that have just bounced against somebody else and temporarily are at zero, but not many of them. So let's see what happens to this curve as I decrease the temperature. So here we go. Drop the temperature, 700, 660, 640, 620, 580. I'm going to get all the way down to 420. Let me see. This is about. It's still pretty. Oh, no, I got 380. Let's move it up to my. No, actually, I can do it down to 240. Come on, 240. Keep on going. Keep on going. There we go. This is pretty much room temperature. Now, see how the curves has changed? The peak is higher, and this is sort of counterintuitive. You'd say, oh, at a higher temperature we're going to have a higher peak, but no, it just means that we've got a greater number of molecules with the average. You can see we've got the same area underneath here. Area underneath the curve is still 1, but it's not quite spread out as much. There's very, very, very few molecules at 1,000 meters per second, and almost none at 1,500. We still have our zeros, so the peak goes up because we have a greater number of molecules with this average temperature. Let me put in a diagram. And this would be a colder temperature. Yes, we still have variety in the number of molecules, but notice the range isn't quite as great. It's a narrower range, so our average will have a larger number of molecules, as you see from this peak. In fact, in this case, the average is about 426 meters per second for the average molecule here. Now let's go back. That was 426. And let's go back up to our high temperature, which we were at, which was 720. Let's zip up, and that way you can see the curve change again. There it goes. Look at that. Beautiful. Amazing. This is a wonderful simulation. There we go. 660. Now we're at 720. Now I'm going to put in something that's a little bit beyond AP, but I think that you may enjoy, especially if you love mathematics, because this is really interesting. At least to me it is. Right now, we've got a temperature of 720. And we have I'm going to write it down right now, an average speed of 738 meters per second. Okay, so 720, that's, like I say, a pretty high temperature, and of course, a high average speed. Now I'm going to drop the temperature down, and again, we'll watch this curve go up, and that's worth doing. So I'm going to drop this temperature down to our low that we had, which was 240, pretty close to room temperature. Warm room, but still pretty close to room temperature. So now we're at 240 kelvins, and again, our peak is way up here. And that's my new temperature, 240. And notice I have an average speed that's 426. Now this is where I'm going to bring my calculator up. Those of you who are good with math will be able to see this. I've already done these calculations to make sure they work, but this is interesting. Now, the original temperature, our high temperature, was 720 K. You don't want to be there. And warm room temperature was 240. And you can see why I picked these two numbers, because the temperature was 3 times higher. Using kelvins, what it really means the temperature was 3 times higher. Now, let's look at the speeds. The high speed that I wrote down was 738 meters per second. Now I'm going to divide by now the average speed at the colder temperature, which is 426. Now, notice our speed was down to 1/3. Our temperature was down to 1/3, but our speed didn't slow down correspondingly. In fact, let's see what our result is. Our result is 1.7. So the speed went down by a factor of 1.7 rather than a factor of 3. Now, here's where the fun math comes in. I'm going to take the second function, square root of 3. 1.73. Evidently, these little bouncing molecules know the square root of 3. They can calculate it. So I'll leave that to you to figure out in terms of kinetic energy. Again, this is beyond the AP. Maybe in your college class they'll ask you to explain why this happens. Okay.